Good morning, everybody, and welcome to this 15th edition to the Code of the Month organized by CASTIEL 2. We have the pleasure to host the energy-oriented COE, or ECO for short, today, and Stefan Collett will give a talk on the code Parflow. Stefan is the head of the research group Integrated Modeling of Terrestrial Systems at Jülich Supercomputing Center, and Parflow is a hydrologic code, and in ECO it's used for modeling for hydrological energy generation. So, Stefan, the floor is yours.
Yeah, Gautam, thank you very much, and I apologize for the camera that is not working. Just a quick correction. So I'm not at the Jülich Supercomputing Center. I'm at the Institute for Bio and Geosciences, just to be transparent here. So I'm going to talk about water modeling for hydropower with Parflow in EoCoE. And I would like to acknowledge, of course, my colleagues from the Research Center Jülich, and also all the EoCoE partners that are contributing to this effort. And I will get to the partners, in the coming slides as well. So what I've tried to talk about today is about Parflow in EoCoE, what's our role in EoCoE, and then I talk a little bit about the background of water for energy in the context of the terrestrial water cycle. I'm gonna talk a little bit about the specifics of our integrated hydrologic model Parflow, and how we are implementing human systems impact modeling with respect to hydropower infrastructure into Parflow. And I think what might be also interesting to people, I will talk about our approach to performance portability and the exercises we did to demonstrate exascale readiness. And I will provide a brief examples on prognostic water modeling at the continental to global scale. So briefly about Parflow and EoCoE. So EoCoE, as you know, is now in its third phase, and we have been very fortunate to be part of EoCoE starting from the first phase. And so we in EoCoE 3, we are one of 5 exascale lighthouse applications optimized for European exascale infrastructure, and we want to tackle societal and scientific challenges in the domains of fusion materials, water, and wind for energy. And we are so in the, let's call it the water silo, with Parflow and many colleagues from University of Roma, University of Trento, and RIA, the Erlangen-Nuremberg University, and also CNR in Italy, who are contributing very important technologies with respect to solvers, advanced solvers, as I said, hydropower infrastructure modeling, and also in situ technologies. So I believe everybody has seen this kind of cartoon, probably also already in high school, which depicts the terrestrial water cycle, and I will not go into detail here. I just want to highlight a couple of things that are important for water for energy. So in general, what you observe in reality is you have advection of moisture from the ocean onto the continent, and generally what we observe on the continent is that precipitation on average over large space and time scales is larger than evapotranspiration. That means that the continent is a sink for atmospheric water, and that holds actually also over quite arid regions. And that means actually that the continent has to get rid of excess water, and we take advantage of that by, for example, building reservoirs that we can use, for example, for water supply, for example, for agriculture, but also, of course, for hydropower production. Of course, in this drainage of the water over the continent, let's say from recharge areas, in the mountains towards discharge areas along the oceans, the river corridors play a major role, and of course also groundwater plays a major role because it supplies base flow to the continental rivers. So actually the discharge we observe in rivers is not by direct runoff on the land surface, but it is by far mostly stemming from base flow in the subsurface supplied by groundwater. So meaning if we want to understand and basically predict also river discharge for example, reservoir management for hydropower, we have to understand the water continuum from groundwater across soil water towards the surface water. This is depicted here, and I zoom in a little bit. So, for example, here we have streams, lower order streams that provide discharge, to river corridors, and this is done mostly by base flow, which is converging along river corridors and then basically outcropping in these continental river systems. And of course, what we do is we dam these river systems to generate reservoirs and use these to generate hydropower. That's what we are dealing with here in EoCoE3, and we do this from the local scale to the, well, actually global scale. That is the goal. So the problem is what we are facing now is that due to global change, this water equilibrium, this continental water equilibrium is changing. The snow ice regimes are changing. The precipitation regimes are changing. ET is changing because of climate change. On top, we have an ocean that is basically rising. So this signal is propagating also into the continents. And that means that the water equilibrium from the recharge zones to the discharge zones is changing on very different time and space scales. So, for example, that would also mean that here along river corridors in mountainous regions where we have the reservoirs, for example, base flow will change, which will change reservoir management on short and long time scales. Okay. So what are the challenges we are facing here in doing water modeling from the local to the continental scale? We have an unprecedented variability and heterogeneity at all scales in terms of actual flow and reactive transport from seconds to 10,000s of years. We have to represent the hydrogeology of the subsurface, which varies from centimeters to thousands of kilometers. We have tectonic structures we have to represent at different scales. Topography varies, soil cover varies, land cover varies across these different scales. So we're talking 5, 6, 7 orders of magnitude. We have to implement human interventions, of course, right? Because they influence the natural cycles, and we have to use water from the natural cycles to actually fill our reservoirs. We have to represent dams. We have to represent groundwater, surface water abstractions, for example, from pumping wells. We have to account for agriculture, irrigation. They are in direct competition, for example, with respect to water for hydropower. And we, of course, have to also represent shallow drainage infrastructures like tide drains that actually are very important in agricultural landscapes. For all this, we need data and observations, and we get those from in situ remotely sensed tools. We need those for all of the above. We need them also for groundwater recharge, base flow, and stream discharge. Some of them are actually not really observable, like base flow. We have to invert those from models in combination with observations. We need water levels estimates, soil moisture estimates, storages to validate and also calibrate our models. This is true also for evapotranspiration, also nutrients and contaminants. And bottom line is, well, these observations are often sparse. They are often actually not available, or they might be even erroneous. So it's a really underdetermined system we are dealing with. And these space scales are also here, time scales. This range of time scales also depicted here in the figure on the right. So it's an enormous challenge we are dealing with here. So what's the status quo currently? Currently, at least at the global scale, we have global water models that try to tackle exactly these challenges, which are mostly parameterized. So they're not really based on, let's say, a combination of continuity equations and movement equations. They are parameterized models. And what we see when we compare results, for example, here with respect to groundwater table or level estimates, we see that In comparison to measurements and also with respect between different models, we see extremely large uncertainties. So we see that large parts of these models provide uncertainty estimates on the order of tens of meters, sometimes even on the order of hundreds of meters. So this is a major challenge because these uncertainties directly propagate into uncertainties of base flow, river discharge, and then ultimately also, let's say, water management strategies. Okay, so we are tackling this uncertainty with physics-based water models, meaning we try to implement models based on a combination of continuity and movement equations, providing also the appropriate boundary and initial conditions. So our approach here is Parflow. It's an integrated hydrologic model which has been originally developed at the Lawrence Livermore National Lab since the 90s. The current core developers University of Arizona, Lawrence Livermore Lab, we are in Jülich and also Princeton University. It's an open source, open development effort. So everything is available to the developers and users. It's a PDE-based model of 3D variably saturated subsurface surface water flow, including human interventions. So we call this the water continuum approach. Parflow also integrates a land surface model, which accounts for the water energy balance at the land surface, for example, related to evapotranspiration. There is also a parallel reactive transport model connected to Parflow. What we also have, but not in main, is a coupled energy transport model and adaptive mesh refinement approach with P-Forest. Over the past 15 to 20 years, Parflow has been coupled to various other land surface and regional climate models to really close the water cycle from groundwater to the top of the atmosphere and understand how feedbacks work in the system, how climate change impacts storages, and how also humans intervene into the system. And we have done most of this work with external couplers, which are not relevant at this point here. Very important, though, is data assimilation approaches that we have also integrated with Parflow, where we're able to merge the model with observations, with in situ observations and also remotely sensed observations, which is really important also for quasi-operational forecasts we are doing. And I will get to this a little bit. We optimized, of course, for massively parallel supercomputers. It's a self-centered finite difference, finite volume scheme with implicit time integration. We use Newton-Krylov methods with multi-grid preconditioning. We have parallelism implemented. We have heterogeneous parallelism implemented based on MPI accelerator combinations. I will get to this also in a second. And we have done this this kind of implementation via a performance portability layer, which I will describe also in the coming slides. So it's a C code, or a combination of C and C++ code. We also have a Fortran component there with respect to the land surface model, and it's available on GitHub. Our colleagues also, mainly in the United States, also provide emulators for Parflow, which is quite useful also in quantifying uncertainties. Okay, what's nice is we can test hypotheses, so we can basically simplify this model to a very simple thing like a lump model type, of which is used for example, also in this parameterized global water models, or we can really do the full 3D continuum approach from groundwater to the land surface. Okay, so what's the challenge for us is that we always have to provide a spin up. We never know completely the initial state of the system, of course. So what we do is we have to bring the system into what we call a dynamic equilibrium with the water forcing at the land surface. We refer to this as spin up, and this of course takes quite some time because there's a lot of time scales in the model, especially at the longer time scales, which make this spin up simulations quite cumbersome. So what we do is we initialize the system with some arbitrary pressure distribution or moisture distribution. then we start the simulation, and which happens then is that you see that a little bit here in this animation is that, well, the river corridors start to appear. So the system is kind of developing naturally based on the physics and the water forcing at the land surface, and then step by step is approaching this type of dynamic equilibrium, which we can then use to initialize our let's say forecasts at different time scales, or also like projections at the climate time scale. Okay, so this is what you see here on the right. Okay, I quickly will talk about the human systems impact modeling with respect to hydropower infrastructure, which is done in collaboration with our colleagues at the University of Trento and also at ENRIA with respect to in situ. So this is a true challenge. I mentioned that before. We have a global distribution of reservoirs and river barriers. Globally, they are extremely heterogeneous. The information on these infrastructures is fragmented in different databases. What we need to represent these infrastructures with models, for example, network models. Here, an example of hyperstreams from the University of Trento, where we simulate, for example, tunnel infrastructures, aqueduct infrastructures, the reservoirs themselves, and so on, which are interconnected and managed. And of course, we need to have hydrologic forecasts that are very accurate to, for example, also account for extreme events, which are very important in managing these systems. And of course, we are interested in a forecast of river discharge, actually for reservoir management and hydropower management. But we are also interested in the other feedback, how these systems actually influence the natural cycles, and especially on intermediate time scales, let's say on the order of decades. Currently, we are collecting data sets and represent the systems topology across these artificial infrastructures. The work focuses on designing a global data set compatible with the modeling framework that we are using right now. And so we are collecting this information, as I mentioned, from these different databases globally. And we currently have a preliminary test case of these data sets completed over the Italian Alpine region. And you see here like a zoom in over the Austria province on the left-hand side, where you see, for example, different hydropower plants, reservoirs, stream networks, and also channels on the left. So it's a quite complex system. And the image on the right shows the preliminary stages of the development for the global data set, where the red dots represent reservoirs and green dots represent actual hydropower plants. Okay. So I have to move the slides. Here it goes. So we are also developing and integrating an impact module coupled with Parflow. This coupling happens with in situ technologies that are provided by our colleagues from ENRIA in France. So here we basically couple Parflow via these in situ technologies and represent, for example, different releases or intakes of reservoirs via nonlinear sink source terms in Parflow, which is also quite, let's say, advanced with respect to the different solver technologies. Okay, so next slide. I want to quickly talk about our efforts with respect to performance portability and also exascale readiness that we have been working on for the past years. So we have implemented an approach for performance portability based on a so-called performance portability layer, where we abstract repeated code patterns into this dedicated layer. So what we do is we write all hardware-dependent code inside this dedicated performance portability layer, keeping the core logic hardware agnostic. And by core logic, we mean really the domain specific part of the code. We keep that hardware agnostic, and that means that we actually reach quite a high degree of performance portability and separation of concerns. Thus, the domain scientist does not have to worry about which hardware he is using. So the end user ultimately just configures the system using different CMake options to enable different backends to this performance portability layer with respect to CPU native CUDA or CoCoS, and he or she is doing that at build time. And then basically the PBL is leveraged to map API calls to the target backend in a very seamless fashion. This is depicted here in this schematic. So you have this domain-specific code here, which the domain scientist sees, and we have this performance portability layer that separates basically the core logic from the hardware. And what the end user is doing, basically, or the domain scientist is doing is he's using CMake options to connect it to different backends. Here, for example, CPU, CUDA, or CoCoS, and also different memory allocators and memory managers like Umpire and RMM. So in the code in Parflow, because in C, this performance portability layer is implemented in terms of C macros. So you would see, for example, a C macro for a three-dimensional loop over IJK, where the function actually is passed as an argument. So if we have the native CUDA, so then basically the loop body is passed as a lambda function, and this is done in a very similar fashion in case of CoCoS. Just as a brief example here. This is of course specific to a Parflow in C. You know, if you do C++, it would look a little bit different, of course. In order to demonstrate this performance portability, we did some scalability exercises on Jules Booster and also on Lumi on the AMD machines. What you see here are the results for the single node performances. Here you see the performances for the native CUDA with RMM and CoCoS CUDA with RMM. At the baseline here you see the results from the EPIC. What you see here that we get quite some speed up. But what you also see is if you basically have full performance portability via CoCoS, that you don't achieve performance, you take like a performance hit. Relative performance with respect to the baseline is on the order of factors 36, but this is of course also due to the lack of optimization, you know, on the CPU, on the pure CPU side, for example, where we do not use memory management. So how does it compare to Lumi? Here, oops, now it's moving. Here we use only the CoCoS enabled implementation, and we see actually very similar results to also Jules Booster from the ULI Supercomputing Center, maybe even a little bit better performance. With respect to the baseline, we get a speed up of about 16. Again, just keep in mind that the CPU baseline is not really optimized. For example, again, we do not have memory management here. Okay, to demonstrate exascale readiness, we're participating in the early access program of Jupyter, the new exascale machine at the ULI Supercomputing Center. And so we've performed a number of different strong scaling tests based on the various scaling variants that were part of this URI program, going from 1 node to 816 nodes, basically the full machine. And what we see here really is that Parflow is actually scaling over the full machine in a quite reasonable fashion, as you see here on the right side in the plot. and which ultimately gave us also the certificate recognizing the exascale potential of Parflow and also suitability for Jupiter. Then we did a development on JEDI. This is the exascale development instrument implementing the Grasshopper super chip. At this point, the deployment on JEDI is actually complete, and we were able to perform a comparison to a Jules booster, which you see on the right side. You see that actually the JEDI achieves a maximum speed of more than factor 2 over Jules booster, but you see also a very strong flattening of the performance curve here, which is mainly due to problem size being referenced to Jules booster, where we have a memory that is more than a factor 2 smaller than that on JEDI. So we are not able, with these problem sizes, we are not loading the super chips enough actually, which is one of the reasons for this flattening, for this very strong flattening of the performance curve. Okay, so here I summarize just some insights. For us, this performance portability layer is most useful. If you do this with COCOS, you of course have ultimate, well, maybe not ultimate, but you have extremely strong performance portability at the cost of some performance, which I would expect that we can optimize that also in future. The native CUDA with a pool allocator outperforms generally COCOS CUDA for many different reasons, which I will not go into here in detail. And then there are also some comparison of COCOS HIP on the AMD Instinct accelerators, which will also not go into detail here. So now with these tools, with these developments, we are able to do things we were not able to do before. So we can now actually scale up our simulations from the alpine scale to the continental scale, also to the global scale. We currently have implemented a global scale prototype at 1 kilometer lateral resolution with 15 vertical layers in the subsurface. This results in about 10 to the 11 degrees of freedom. We also have the respective boundary conditions in there. And we informed this prototype with the global hydrologic and soil information, which will show in a second. So the spin-up is on its way, so to speak, with effective recharge estimates, precipitation minus evapotranspiration at the top. And we are now doing actually production runs really on the Jules booster machine with 320 NVIDIA GPUs. So we are able to complete 1 year simulation in approximately one day, which is actually really good. So just to give you an idea about some of these input data sets, here on top you see a geologic maps from Glimpse, which is a global data set. We overlay over that geology the soil information. And then we drive this model with effective recharge estimates. You see that here at the bottom, where we got the data from a model in the comparison project from the World Climate Research Program. Here, we have to interpolate the data from 50 kilometers to 1 kilometer. So this is also something we need to improve in future. So what's the outcome? Now we actually are able to simulate groundwater, the water continuum from groundwater to surface water at a kilometer scale resolution. So we're basically obtaining all states and fluxes everywhere, and we are able to derive diagnostic variables such as groundwater table depth at each pixel. So what you see here is actually the groundwater table depth, so the water level below the land surface. And you see already here, you get an idea about the great detail we are achieving with these first-time simulations. This is, of course, extremely relevant for water for hydropower. We are able now to resolve river corridors over 3 to 4 order of magnitudes. We are able to simulate groundwater surface water interactions along these river corridors. thus we are able to actually provide discharge values for reservoir management, and we are able also to interrogate the two-way feedback of these human interventions on the natural water cycle. Again, at these local resolutions everywhere. Okay, I'm done for today. Here I just summarize some of the resources related to Parflow, and I'm happy to answer any questions. Thank you.
So thank you very much, Stefan, for this very interesting and comprehensive overview of what Parflow does and how it can be used. And the floor is open for questions, so either in the chat or in the specific module here.